Hello and welcome to Keystone Shooters. Today we are going on to a new topic of integration, and we're going to start with the basics of how to integrate X. Before we begin, I'd like to talk about the meaning of integration. I think it's very important to understand why we use it. The general formula, integrating X, and two very basic examples to sort of give an introduction to this topic. All right, beginning. What is integration? So we see these two here, and I will zoom in. But you may be thinking, why are these even here? So integration pretty much refers to the area under the curve. So as we can see here, this black line here is like a function, and the area and integration wants to find the area under this curve. All right. So let me zoom in a little bit. Each rectangle represents an area of a rectangle. And it's pretty much, we use these rectangles and use multiple of them, as can be seen here, to pretty much provide a guesstimation of the area under the curve. When we have a smaller amount of rectangles, as can be seen here, comparison to here, which we will tend to later, we can see points where there is overestimation of the area, as highlighted by these green shaded areas, and there's also points where there is underestimation, seen here. So this is when we have fewer numbers of rectangles. Let's go down. All right. So we're gonna zoom in here. Now you can see here, I'm sorry for the um non-continuity of these rectangles, such as here and here, a bit of a slant. I did do these by hand, and there is a lot of them. So I was not able to, unfortunately, get them all great. But we can sort of get the general gist. As we can see here, look how many more rectangles are than compared to here. With that, this has provided us with a much greater area estimation of under the curve, as there is a lot less amount of overestimation and a lot less amount of underestimation in comparison to here. So the general principle is the more amounts of rectangles we put, the better the estimation of the curve. All right, so you would say, why do we want to even worry about the area under the curve? Well, it's really great for use of probability. So probability, we need integration and probability because that the area under the curve directly is the probability of achieving an outcome. So this is why we use integration to find the area under the curve, and thus usually use it for tools such as probability, estimating the probability of a function. So this is the general formula here. So this is how we represent integrals by this sort of double hooked line here. As you can see here, there's a hook here, there's a hook here. This looks like a fishing hook, but just on two sides superimposed with one another. Sorry, mirrored. And then we have xn a times xn dx. So let's break this down. So xn is our function, a is a constant times by our function, and d of x means we're integrating with respect to the parameter x. Awesome. So what is this b and this d doing here? So this b and this d is sort of setting a range of integration. So let's say, for example, we could say, going back, we could say that this is b here and this is D here. So it would say we're integrating along this range. We're finding the area from B to D here. That's what B to D represents. That's awesome. So what do we do? So integration, just a general sort of idea about it is it's the opposite of differentiation. So instead of minusing one from the power, we're plusing one in this case, as can be seen here. Awesome. So as the a is constant, we can take it outside. And what we'll do x to the power of n plus 1. So we add 1 to the power, but make sure we divide this by n plus 1. Awesome. And then what does this mean? So we have square brackets here, and it's important that they're square from B to D. This means we will sub in D into the X component and also B. But when we do this, we must minus them from each other. So we must do D to the power of n plus 1 all over n plus 1 minus B to the power of n plus 1 all over n plus 1. And it's important that we put brackets here because we have a constant A at the front. We can also integrate without these bounds here. We can just do general integration and it changes a little bit. So let's just do that. Let's say we have x and d of x. Okay, let's forget about the a, it doesn't really matter. And we have no bounds, as you can see here. The integral for this would be x to the n plus 1, so keep all that the same, that principle the same, all over n plus 1. All right. And then what we do, we add a plus c. So what does this c represent? This c is a constant. Why do we do this? Because we said integration is the opposite of differentiation. Let's pretend this x to the n was the derivative and we want to find the original function. We can do that through integration. We can get the x to the n and integrate it, and this would be the original function. But why do we plus the c? Remember, if we have a function, I'm just going to provide you a random function, f of x, okay? Equals, let's say it was equal to x squared plus 2, okay? What's the derivative of this? Not the integral, the derivative. The derivative here, we take f dash of x, it's just equal to x, remember? It's equal to x. So the 2x, the 2 here goes to 0, remember, because it has no parameter associated. So if we see this as f dash of x, if we see the integral as f dash of x, okay? And when you integrate it, it provides the function f of x, right? But in the derivative, if we were initially given the derivative, if we were initially given the derivative f dash of x, we wouldn't know when we integrated that there would be a plus 2. We'll get 2x, so we'll get x squared. Awesome. And then we have the plus c because that 2 does exist, but we can't know it. So that's why we add a plus c. We don't add a 2, but we just add a plus c when there's no bounds. When there's bounds, we don't add this plus c. Awesome. How do we integrate x? Awesome. So let's use that exact same formula. So the derivative of x with no bounds in this case is x d of x. What is that? What's the same as? Remember, x is just the same as x to the power of 1. It's the exact same thing. So what do? We go x over 1 plus 1, because remember, it's n plus 1, and then divide it by n plus 1 again, and we get plus c. Awesome. So eventually, we just simplify that, x squared on 2 plus c. So that's the integral of x. Very nice, straightforward. What's the integral of x with two bounds in this case? B and D. Remember, B and D being, in this case, our area here. We want to find the area here, the probability of being within B and D, you can see it as with a function. Well, simply it's just x squared, but we go from B to D, so we sub in. Oh, my fault. There should not be a plus c here. That is a mistake on my end. Yes, so simply there is just x squared on 2 from B to D. So we just sub in D and B into the x parameter. So it'd be D squared on 2 minus B squared on 2, and that is simply our integral. Awesome. So now we're going to go on to the last section, two basic examples. So we have 3x squared here. And this is how the 3x squared graph looks like. When we're integrating, we're saying, and cos in this case, we have no bounds. You see here, we're saying, what's the area under the curve for all parts of the function? What is it? What is that? So we're looking at all this area here and continuing all the way underneath the curve. Awesome. So when we integrate that, we can take the 3 outside because it's a constant. And anything that's a constant and doesn't have the parameter x, we can take outside. Even if this was a y, if this was yx squared, we could take the y out because we're only integrating with respect to x. But let's just say it's 3. So we have 3 over x to the n plus 1, 2 plus 1, over n plus 1, 2 plus 1 again, plus c, because remember, we have no bound here, so we have to add a constant. So we have 3 on x, 3 on 3 plus c, that simply cancels out, and we get x3 plus c. Awesome. So now we're going to the final example. We want to integrate x. We did that before, but now we want to do it between the range of 3 and 6. So if x being a line like this, 3 and 6 is the area between 3 and 6, and it's the probability of achieving a result of 3 to 6. So 3, 4, 5, 6, or any number in between. So when we integrate this, it becomes, as we found before, x squared on 2. So then we sub in 6 squared on 2 minus 3 squared on 2, and we get 36 on 2 minus 9 on 2, and that's simply 27 on 2. Awesome. So that is the end of this video. I hope you found it useful and got something out of it. We will be continuing this series on integration, and best of luck with your studies.